Okay, so in this video we're going to learn about oxidations. So in general chemistry we talk about oxidation in like the extremely technical sense of the word, where you're looking at literally electrons lost, electrons gained, and we talk about, eventually we're going to use that to show how we do batteries, and we talk about voltages and all these different types of things. Organic chemistry, we take sort of a different approach. I'll try and tie it back into what we learned in general chemistry though. So an alcohol, or if you want to look at the carbon atom of an alcohol, has a particular oxidation state associated with it. So if you take into account the different things that are attached, so this and this and this all contribute to the oxidation state. You sort of pretend when you're assigning the oxidation state here that the compound is ionic. I doubt we'll ask you to do this on an exam, but this would count for -1, this would count for +1, and this would count for +1. So any hydrogen counts for +1, and any oxygen counts for -2. So if you want to be really more detailed about it, this hydrogen here contributes the +1, this considered a -2, and sort of the net on this is -1. And so anyway, so the carbon has to end up balancing out that charge. So you have +1 is +2, -1, so we end up with, +1, +1, -1. So we end up getting +1. So we need to balance that out, so we know that our carbon must be -1. So this is, I'm going through this reasonably fast because, again, we're probably not going to ask you anything about it. But so this is -2 and this is +1, which means that this must be +1, and then this is -1 and this is -2, which means that this must be +3. And so the important thing here is, I guess one thing I want to show is, we're calculating the oxidation state just like we did in general chemistry, right? We looked at the things that we knew. And we use that to calculate the oxidation state on the carbon atom. Okay. But so you can just accept that the oxidation state of these carbon atoms is changing. And the oxidation state of the carbon atom is, this is one thing maybe you want to take away, the oxidation state of the carbon atom is dependent on what it's bonded to. And we could calculate it if we wanted to. So if you wanted to travel between these oxidation states, we could do something like we did in general chemistry. We could try and take a metal or try and apply some sort of voltage or something to this and try and actually electrochemically oxidize this alcohol to make something with a higher oxidation state. Just like when we set up batteries and stuff, there is a way to do that. More practically in the lab, you don't want to have to be setting up batteries and stuff to oxidize an alcohol. We have a bunch of different reagents and stuff that can do this. And they can do it reasonably selectively, which is nice. Something you don't necessarily get if you do it electrochemically. Okay, so this is an oxygen with little brackets on it, and it means oxidation. It's not a reagent. It's just saying that I'm going from one oxidation state to another oxidation state. It means I'm going from a lower to a higher oxidation state. That's what that means. We won't be looking at reduction, but reduction has an H. So if you're going in the opposite direction, we won't learn any reagents for this. But if you're going in the opposite direction, those would be considered reductions. And there are reagents that allow you to do reductions, and also you could do them electrochemically. And so these are just symbols to indicate which direction you're going in terms of oxidation or reduction. An O means you're going to a higher oxidation state, and H means you're going to a lower oxidation state. We're going to learn how to go in one direction, and in the second course, if you take it with me or Samoylenko or one of the other instructors, they'll teach you about how to do reductions. Okay. So if I want to oxidize this, I've got ethanol. I've been out drinking. Actually, Actually, it's an interesting one to talk about. But one way to oxidize this is to use chromic acid. So this is a very, very strong oxidizing agent. You'll notice it has lots of oxygens on it. Chromic acid is really nasty stuff. Like if you spilled it on your skin, you would, depending on how much you spilled, have to go to the hospital. So looking back here, what we notice is that in the first, let's see, let me go back to this. In our first situation here, we have an alcohol. So an alcohol is the lowest oxidation state that you can be in. When we move up oxidation states, the carbon has changed charge, and I kind of emphasized that a lot when I started talking about this, but really what we worry about as organic chemists is what's happened to the functional group. The alcohol has now become an aldehyde, so an aldehyde is considered more oxidized than an alcohol. And then in our last bit here, now we have a carboxylic acid. So carboxylic acid is sort of the maximal oxidation state that you can be in if you're a carbon atom. The other thing I'll draw your eye to is that I'm losing a hydrogen each time I go through the oxidation step. So in this first part, where I'm an alcohol, the part that I've highlighted in orange here, you'll note that I have 2 hydrogens. When I go to the second part here, I only have 1 hydrogen. And then finally, I've lost all of the hydrogens directly attached to that carbon when I'm in the highest oxidation state. So each time you oxidize the carbon, you lose a hydrogen. Formerly, you would lose a hydride. It's taking its electrons with it, right? So I'm losing electrons, which is my definition of oxidation to tie it back into general chemistry. Okay. But, of course, this isn't a general chemistry class. What does it look like for us as organic chemists? If I add chromic acid, what you would expect is I would oxidize it sequentially, first to the aldehyde, and then to the carboxylic acid. And you'd be correct, because just like if you're going between oxidation states in a metal, if I'm going from, say, -1, which is all the way to +3, it just makes sense that at some point I'm going to have to go from -1 to +1 to +3. So I'm using the literal oxidation states from our carbon atom at the top. See, -1 to +1 to +3. It makes sense that at some point I have to stop at +1, right? I'm not going to just magically, I'm not going to gain all the electrons at once. I mean, I guess you could reasonably believe that, but that's not how it works. Usually you gain things sequentially, so you're going to have to go through that +1 oxidation state. But if you run this reaction with chromic acid, you don't actually see this. Not isolable. Maybe a new word for you, isolable. Not isolatable. But yeah, you don't actually see this. We only see the carboxylic acid. And the reason for that is that the aldehyde is actually easier to oxidize, so it has a lower oxidation potential than the alcohol. So as soon as this becomes the aldehyde is now more reactive than the original starting material, and it just immediately gets converted over to a whole other color palette. It immediately gets converted over to the carboxylic acid. So you can't actually isolate it out because you're forming something more reactive as an intermediate. And so generally, if you start with an alcohol, what you end up seeing is just, at least for primary, you end up getting a carboxylic acid out with chromic acid. Okay. So if I was doing this in flashcards, short explanation here is this would take me from an alcohol to a carboxylic acid. Now I would note on my flashcard that this is only true for primary. If I take a secondary alcohol and oxidize it, remember what I said about the hydrogens, right? So I've got a hydrogen atom there. If I oxidize it with chromic acid, I'm going to get rid of that hydrogen atom. That's sort of what the oxidation process does. But I've only got one. So it just stops right here. And if that doesn't make sense to you just based on the hydrogen argument alone, imagine that if it were to keep going, well, how would it form the carboxylic acid? In order to form the carboxylic acid, I have to form a bond between the carbon atom, which is here, and a hydroxyl group. So the way I did that when we come back up here, things getting kind of messy, but the way I did that up at the top is I had this hydrogen and this hydrogen. In the first step, I removed one of those hydrogens. Okay, that bond that was once part of the hydrogen became part of the double bond to the carbonyl group. In my second step, I removed that hydrogen and replaced it with a hydroxyl group. So each time you go through an oxidation, you're getting rid of a hydrogen. So in a secondary carbon, you don't have two hydrogens to remove, so you just end up stuck at the carbonyl. So chromic acid takes you just to the ketone. And then if we look at what happens in a tertiary alcohol, what's going to happen here if I add chromic acid? I'm not going to see any reaction. And this is that same argument. If we don't have any hydrogens to start with, so oops, let me see. If we don't have any hydrogens to start with on our carbon atom, there is no way for us to oxidize it without doing something extreme like breaking a carbon-carbon bond or something, which we're not going to look at. Okay, so if we take a primary and use an alcohol and treat it with chromic acid, we get a carboxylic acid out of it. If we take a secondary and we treat it with chromic acid, we get a ketone out of it. And if we do a tertiary, you don't have to necessarily make a flashcard for this if you understand. But if I have an alcohol, I'm going to get no reaction with it with chromic acid. And that's because there's nothing to oxidize. It's sort of, in a sense, it's in its highest oxidation state it could be in already without breaking carbon-carbon bonds. Okay, so remember what I said earlier is like typically if you can think of a downside to a reaction, like for example, if I'm starting with a primary alcohol and let's say that I don't want to make a carboxylic acid, but I actually want to make an aldehyde. Currently, we don't have a way to do that because chromic acid takes it all the way to the carboxylic acid. Of course, chemists have figured out a way to do that because sometimes you do want an aldehyde. As we'll see in the next semester, not in this course, aldehydes are actually very, very useful synthetically. What we can do to achieve this is use a special chromium reagent called PCC, and that will stop us at the aldehyde. What does that reagent look like? So PCC stands for pyridinium. This is what pyridine looks like. It's a benzene ring with a nitrogen in it. Pyridinium implies that it's protonated, or it's part of a salt. Pyridinium chloro, my notes here. There we go. Pyridinium chloro, and then chromate, which is CrO3. So you have here is a salt of chromium. And this special reagent allows you to stop at the aldehyde. And if you look at the mechanism in the book, it sort of explains why that allows you to stop it. It has to do with sort of breaking. It traps the mechanism of the aldehyde because it gets rid of water as an intermediate, is something that forms in the reaction that can continue to oxidize it. But we're not going to get into that. For us, what we want to look at is just that this allows us to take an alcohol, specifically a primary alcohol. That's really where you'd use this to an aldehyde. If you use this on a secondary alcohol, what are we going to see out of it? Yeah, you're going to get oxidation. But yeah, we don't really, there's no reason to do this. PCC, again, this is a practical consideration that you're not worried about, but PCC is going to be more expensive than chromic acid. You're just going to want to use chromic acid. But if you like PCC, go for it. Use PCC on paper. I'm not going to include that in the flashcard deck, but you should know that it will oxidize it. Okay, so yeah, that's the oxidation part. In previous semesters, I've taught the reduction part with it because there's a way to kind of undo all these reactions. They're reversible. But I think traditionally that's taught in the second part of the course, and under our current circumstances, I don't see any reason to make things, make you guys have to learn more. We've already kind of lost a week here. If we have extra time, I think we should probably spend it on NMR. But yeah, so some oxidizing agents. These oxidizing agents that we just learned here, I know I went into a lot of detail on them, but these are super important for the next course. So if you're kind of looking at things to really kind of cement in your mind, be able to do these oxidations, because the entire second course is based around, the course itself is kind of based on functional groups. It's based around these things, carbonyl groups, or carboxylic acids. That's mostly what you learn about in the second course, and they sort of have their own reactivity about them. But having these reactions in your pocket allows you to make carboxylic acids and make aldehydes, and thus be able to do a lot of the synthesis that you see in that course. So, anyway, so that is it. Oh, one more thing I wanted to talk about is this reaction here. Oops. This reaction here. So if you ever drink ethanol, so you go out and you go to a bar and you get a glass of wine or whatever, you cocktail or something, ethanol gets oxidized in your liver to this molecule. So this is acetaldehyde. And then your body, I guess that's less toxic maybe to your body than alcohol is. I'm not totally sure. But ultimately, that gets expelled, in your urine or something. I don't know what the actual total end product is. But the first step is it forms this aldehyde in there. And that aldehyde is actually pretty bad for you as well. And it's one of the reasons if you drink methanol or isopropanol or something, so that enzyme in your liver, so if you look down here, for example, at this reaction, the enzyme in your liver that does this, they talk about this in the textbook, I think. It'll oxidize whatever alcohol you put in there. It's not just ethanol, but the byproduct of it that you get, or the product of it that you get, is acetone, which is nail polish remover, right? So if you were to drink a bottle of isopropanol, you would be creating acetone or nail polish remover in your bloodstream, which is much more toxic to you than acetaldehyde is. In rubbing alcohol, which is methanol, which is the one that people usually talk about, that actually forms formaldehyde in your liver, which is this. And formaldehyde is like really, really nasty. You definitely don't want that in your body. I think it attacks the optic nerve in your eyes, and it will make you go blind. So you definitely don't want to get a lot of methanol in your bloodstream. That stuff's pretty nasty. All of these types of alcohols, methanol, maybe isopropanol as well and stuff, are present in like really trace amounts usually in whiskeys and things of that nature. And they're not dangerous if they're in small concentrations, but you wouldn't want to drink like a glass of methanol. You'd die or have to go to the hospital and be in bad shape for a while. So, but anyway, just a little biochemistry tie in there. The main thing for us as organic chemists is in the lab, how do we take an alcohol and make it into other things? That's what we're kind of hinging on here.